Thank you. Come over to the far side here to do my PowerPoint program. Let's see if you can see this. Welcome to the physics lecture.
All right, is that better? Yeah. Good. Okay, thank you. Welcome to the physics lecture. Now the program, the previous speakers told you what it was, they gave it away. It's going to be the physics IQ test. I made this slide so that you would know that I know where I am today. And I know your first question. Well, you're very worried about about the IQ test. I could see it when I told everybody that it was going to be the IQ test. Can you read that? Old Blondie. The son, I've got a math exam tonight, it's going to be a real tough one. And Berg would ask, are you studying for it? Said, no, that's why it's going to be so tough. Okay. And I know your first question. So what I'm going to do is to tell you about the IQ test. Let's see. For that, I'm going to start by rolling out some. Oh no, I won't, better not do that just yet. I think some of you saw, you can leave a few lights on, that's fine. But we'll do that in just a minute because I've got one more slide that everybody has to see, which we have developed for use in our classes. And I'll get them out one at a time and tell you a little bit about it, maybe show you how it moves or something, and tell them I'm busy. Yeah, we can have a little lights for this. That's fine. That won't interfere with anything. And I'll pose a question involving the demonstration apparatus. I'll do something, and I will. Let's see. I'll tell you what experiment I'm going to do, and then usually it'll be pretty obvious to you what might happen if I do these experiments. But I'll review what the possibilities are. You know, something might go to the right, go to the left, or go down, something like that. And following that, I'll just list them, and then we'll go back and go through the list of possibilities as to what might happen, and you get to vote on what you think is going to happen for the experiment. Okay? You get to vote. Now remember, India is a democracy, like the United States. You can only settle questions like this by a democratic process. So you have to vote. And I don't know is not the correct answer. There's not a correct answer. So you have to vote for one of the answers. All right? Now, let's see, I think we're going to start with a simple experiment, but we can now sort of push this out and push that in there. We'll keep it on this side a little bit there. That's fine. Now I think this should be lit by our spotlights. That's fine. Okay. All right. Well, let's see. Let's do the first question. Yeah, you can go ahead and turn on the house lights also. House lights up is fine. Okay. I've got a super ball here. Doesn't have to be a super ball. Any ball will do. And, in fact, it doesn't even have to be a ball, but that's another issue. I'm going to hold the ball up like this, and then release it from rest. Okay, for your students, guys, this is a physics term, meaning drop it. Okay? Physicists have to have some good terms. You can't leave all the good terms for the psychologists. Okay? So I'm going to hold this up, and I'm going to release it from rest. And drop it. You can keep the lights on. I have the lights. Keep That's right. I'm going to hold it up and release it from rest. And the question is, what will it do when I release it from rest? You see, it could go up, it could go down, or it could stay where it is. Okay. Those are the three possibilities. All right. Looks like everybody has some answer available. I just heard it. Let's try this. Vote by raising your hand now. Who says when I release the ball from rest here that it'll go down? Raise your hand. High. Come on, no guts, no glory. All right. All right, good. Who says when I release it from rest it'll go up? No suckers? All right. All right. How about when I release it from rest it'll stay where it is? None. Okay. Well, let's see. Let's try it and see. Fell down, didn't it? Went down, right? Of course, that's Newton's law of gravity. Right? Everybody knows Newton's law of gravity, right? Right? In fact, if I release it from rest, it will go straight down towards the center of the earth. Right? Well, not quite towards the center of the earth, because the earth is oblate, sort of squished, and it's going around its axis, rotating around its axis. So it won't go quite towards the center of the earth, but it'll be close. That's close enough, right? Okay, good. All right, good job. Everybody got that pretty well. Here's another falling question. Actually, for each one of these questions, I have a link to the page on my website. So I can find and I click that, and it'll go to a page on the website defining that. Well, this is a real simple one. It's a super ball. You can do a whole bunch of things with a super ball. Not much interesting information about it here. But let's see. So we'll just go back the other one, and I'll refer to some of those on occasion. Particularly when there's more information about it, or something that, like a video of what of that particular demonstration, or other links. All right, here's the next question. Let's see. We've got a beaker, a little plastic or Teflon beaker, and there's a mass underneath it. Can you see the mass? It's attached to a spring. In fact, let me just link to this, and you'll be able to see on the page what it looks like from looking up under the into the beaker. Right? Here's the mass and the spring. There it goes. Right? And what I'm going to do now is to hold this up in the air, like this, and release it from rest. You remember from the first question that it'll go down, right? Okay, you remember that. Okay, good. So, that's not the question here, though. The question here is, when I hold this up, what will the mass do? There are three possibilities. One is that this thing might act sort of like a parachute. So when I drop it, the mass, due to its increased inertia, will tend to pull down, and the air will collect in the beaker, and the mass will go a little bit longer on the spring, like this, when I drop it. Another might be, let's see, because of the decreased inertia of the mass, when I drop it, the mass might go up into this cup. Or a third possibility could be that the whole thing will simply drop, just like it is here, with the mass sticking out just a little bit. So when I drop this, when I drop it and it starts to fall, the question here is, what will the mass do? Will it go down? Will it go up into the cup? Or will it stay where it is? That looks like you got your answers ready. It's maybe a simple one. So let's vote. Who says, by raising your hand, that the mass will tend to come out of the cup a little bit? Raise your hand, high. Oh, not very many. Okay, well, all right. How about it'll go up into the cup? Oh, a lot of there. And how about it'll just stay where it is? A few there, all right. Well, that's about 97.5%. Huh. Very unusual. All right, well, let's do it and see. Ready? What did it do? It went up into the cup, didn't it? Can you see that? Actually, on the web, there's a slow motion version of that. If I click there. I hope there's a slow motion version of this. Yep, here it comes. Did everybody see what happened? It went up. Here, I'll tell you what we'll do. I'll start it. Start it going real slowly. Oh, your problem is you can't see it because of this. All right, we'll just rotate this out of the way. No problem. And then if I just click it along, can you see it now? Yeah, that's pretty good. Whoops. Here, I drop it. And there it goes up into the cup. All right. So that. All right. Let's see. This is actually a pretty sophisticated experiment. It demonstrates Einstein's principle of equivalence. Everybody know what that means? The equivalence between gravitational field and acceleration. It's a very sophisticated idea which is involved in general relativity, one of the most complicated topics in all of physics. Let's see. The idea is when something is falling down, accelerating in something like the Earth's gravitational field, it becomes weightless, or weightless, not massless, in the frame of reference. This whole thing accelerates downward because it has some mass and the Earth's gravity is pulling on it. But within this frame of reference, if I made a little sack around it that you couldn't see in or out of, everything inside of there would be massless or weightless, just like if it were in outer space. And because the spring extends, because of the weight, because the Earth's gravity is pulling on it, when that disappears, then the spring pulls the mass up into the cup. And that's the same thing that happens in a space lab or in a satellite going around the Earth, isn't it? Things really are pretty massive up there. I mean, just like they are on Earth. If I took a satellite and put it on a long pole, about 200 miles long, actually, something like 3 kilometers or 300 kilometers above the Earth. If I just took that pole, hoisted the satellite up there, and then removed the pole, would it stay there? No, it would fall right to the Earth. The reason why it stays there is that the rocket makes it go parallel to the surface of the Earth, and it's falling towards the Earth. So everything that happens in a rocket, you've seen these guys hold out a ball and release it and it stays there, right? The reason why is because the rocket is falling towards the center of the Earth. Interesting idea. Sort of a strange idea, isn't it? The rocket is falling. That's the general theory of relativity, the principle of equivalence, which is the same thing as this experiment. All right. Here, we just leave it there, it's fine. All right, I have a slinky spring. I'm going to hold it from one end here. Oh, okay, oops, that's a high one. See if I can get onto that thing. Can I get onto that? Thanks. Oops, I don't. What we'll do is this. All right, thank you. Yeah, rotate. All right, excellent. It adds a little danger here, an element of danger. Hello. All right. All right, I'm going to hold the slinky spring up. And you can see the bottom end now, right? and I'm going to release it. I'm going to let it go. Now, according to the first couple of experiments, it will eventually fall to the ground and be compressed, won't it? Okay. Well, this question involves how it gets there. In particular, let's see, what will the bottom end of the spring do, the slinky, when I release the top end? There are a couple of different possibilities. One is, when I release it, the bottom end will start to come up and it'll compress and then fall to the ground. Another possibility is that when I release it, the whole thing will fall to the ground, and when it gets to the ground, then it'll compress. And the third possibility is that it might, well, the bottom end might just stay where it is for a short period of time, and then move downward, presumably. So the question is, when I release the top end, what will the bottom end do? Will it come up initially? Will it start to go down initially? Or will it stay at the same place where it is now initially and then move later? Everybody ready to vote? All right, well, let's vote. Let's see how this one comes out. Who says the bottom end will tend to come up initially? Raise your hand, high. Good many there. How about the bottom end will tend to go down initially? Raise your hand. From there, okay, and how about it will stay where it is initially? Okay, now you guys aren't all voting. All right, you gotta vote. Let's try this again. When I release the top end, who says the bottom end will come up? Raise your hand, high. Okay, good. How about the bottom end will start to go down? Raise your hand, high. Good. How about the bottom end will stay where it is? Raise your hand, high. All right, that's better. It's about equal numbers. You ready? On the count of 3. 1, 2, 3. What did it do? It stayed, didn't it? Thank you. Let's try this again, so everybody can see, everybody who blinked. All right, ready? On 3. 1, 2, 3. All right. All right, thank you. That's a little bit of a surprising result, isn't it? Let's see. When I release the top end, the real question is, how does the bottom end know? That's a serious question. How does the bottom end know? Let's see, let's look at this thing. Here's the spring. How does this turn know that I released it? Well, this turn only knows when there isn't as much tension pulling it up, doesn't it? And that only happens when this turn moves down so that they're closer together, isn't it? So let's see. If I'm holding the top end, the second turn only knows that it's been released when the top end no longer experiences my upward force and it starts to fall. In that case, the third turn still doesn't know, but when the two first and second turns hit and it gets released and then it starts to go down, then less space between these two. So the third turn knows, then the fourth turn knows, and then the fifth. Did you notice how it fell? One turn at a time, wasn't it? Kept on going like this until it got down to the end, like this, and then the whole thing fell. How many of you noticed that? Maybe we got to try this again here. Notice that. That's really sort of a strange phenomenon, isn't it? Did it work that way?
Yeah.
Okay. When we first discovered this, started playing around with it, we wrote a paper and sent it to the American Journal of Physics. That's a teaching journal for the physics teachers in the United States, but actually worldwide. Actually, a lot of Indians who write articles in the American Journal of Physics nowadays. And the editor looked at our article and returned it, rejected it. And he said that was outrageous to ask such a question of a bunch of physics teachers. Well, here's something that I didn't tell you at the beginning of the IQ test. The questions were selected because they're counterintuitive. They have a counterintuitive element, sort of maybe a trick to it, but you don't want to say trick, that's bad. It's counterintuitive. There may be good reasons why any of the answers could be correct. And so, when I give this program for a bunch of physics teachers or physics professors at universities, about 1/3 of them give each answer for this question. They don't all get it right. And nobody, and I told them the story, that the editor of the journal rejected my paper because he said it was a disgrace to ask such a stupid question of physics professors. And most of them didn't think it was stupid, particularly the ones who got it wrong. And even the rest weren't offended that I asked them that stupid question. Let me tell you a little bit more about a few of the questions that we're now going to get into. In teaching physics, how many of you guys are taking how many of you have taken a physics course yet? Raise your hand if you've taken physics. Few, right? How many of you are taking a physics course now? A good many there. A few more, okay. How many of you are going to take physics in high school? Or if you haven't? Now more hands should be showing now. Right? Physics is a good topic. But one way that researchers have shown that people can learn physics better is by using experiments like this. And by thinking about what happens in the experiment before you actually do it. And then using the experiment to see how well you are at thinking about something and how well you argue for how you use the ideas and laws of physics in explaining things like this. So that's what we're going to do today. We're going to go through and look a little bit at the ideas and laws of physics, and we'll see how they apply and how we think about them in terms of these various experiments. Well, we'll give you another chance here to do a falling type experiment. All right. This gizmo is called a funnel cart. Got a little ball put in the funnel here, and it is spring-loaded. So if I hold it here and let the spring go, it shoots the little ball right up, and it comes straight down into the cart. Let's see. I can also go to our funnel cart experiment here on the web. Let's see. Here's the question. Whoops, be careful. Suppose that I take the cart now and roll it along the track. When it gets to a certain point down here, there's a little mechanism which causes the funnel to shoot up in the air. So it would shoot the ball with it. And the question is, with the ball in there, the cart rolling along, the ball goes up. Where does the ball fall? Does it fall in front of the cart as it's rolling? Does it fall in back? Or does it fall in the funnel? In front, in back, or in? I hear a difference of opinion, which apparently can only be decided by a vote in a democracy. So let's vote. Who says, when I push the car along and the funnel ejects it vertically, that the ball will fall in front of the cart? Raise your hand high. No guts, no glory, right? Yeah, I already said that. All right. Who says the ball will fall behind the cart? Raise your hand. Good many there. Okay. Who says in the cart? All right. Let's look. Looks like about 50% say in, and the other ones are divided between front and back. Ready? You can cheer for your side. It doesn't matter. It doesn't matter how fast you push it. Slowly or quickly. Here's what happens. The ball gets ejected vertically with respect to this cart moving along. It's moving at the same horizontal speed, isn't it? So the ball always stays, as it moves, it always stays directly above the funnel and falls back in. That's an important idea known as separation of coordinates in the physics world. Let's see. Do it once again. Where's another experiment? Let's see. Can you show me an experiment where it would be like you were sitting on the cart when this whole thing was happening? What would it look like? See, if you're sitting on the cart, it's like that, isn't it? Right? How about another experiment where you're off the cart looking at this, a big one? Here's this one, isn't it? Now I'm on the cart doing this, but if there's somebody up off the surface of the world, of the earth, still in space and watching this, what they'll see is the ball will be directly above the cart moving along, because they'll see the whole world moving. Look, down at this level, it's something like 900 or 1,000 miles an hour, isn't it? So they'll see the ball going in a huge arc. It's really going pretty fast. This experiment tells us a little bit about the ideas, some ideas about changing frames of reference. How you see something from a different reference. Like here we're watching this from the frame of reference in which it's happening. Right? When we do it this way, we're watching it from an external frame of reference. We're watching the ball go straight up and down, but this frame of reference is moving. Let's try something here. I've got an experiment on the web. Yep, here it is. Find it. Let's see. If I click down here, maybe we should move it, rotate this a little bit. Excellent, yeah. Everybody see the screen now? What you can do, take your hand or a piece of paper and hold it up so that all you see is the funnel cart and the ball, and the bottom is blocked off when the experiment starts. Oh no, I didn't want to do that one. Well, this is just the maybe it isn't going to do anything. Let's do this one. Uh-oh. No, it isn't doing anything. Let's see. Right. I'll do it again. Block off everything below this point once with your hand or a piece of paper and watch it. That's just like you would be sitting on it, on the funnel cart, watching it go, isn't it? We took this picture with the funnel cart moving along and a TV camera moving along with it. All right. All right, let me get rid of this. And let's try another experiment with the funnel cart here. If I take this weight, it's a heavy weight, and put it over a little pulley here. Okay, now, that's right, just leave it hang. Okay. Now when I let this go, that weight's pulling on the funnel cart, so the cart will accelerate that way, according to Newton's laws of physics. It goes faster and faster. Can you see that? Okay. Now suppose that I load it here, so when it gets to this point again, it'll release the ball. Where will the ball fall? In front, behind, or in the cart? I still hear a difference of opinion. Everybody knew, though. Who says in front? Raise your hand. No suckers? Oh, nobody? Right. Who says in back? Raise your hand. Okay, good many there. Who says in? Raise your hand. Raise it high. No guts, no glory. I already said that. All right, ready? All right, it falls behind, doesn't it? Let's see. What's happening is the cart is going faster and faster, isn't it? When the ball gets ejected, it has a certain velocity in that direction, but the cart is moving faster and faster in that direction. So, the ball gets behind, doesn't it?
All right.
Good. That was a pretty simple one. Most of you got it. There's more than one way to accelerate that cart along the track. Here's another way. Well, where will it fall? In front, behind, or in the cart? Still a difference of opinion. Let's see. Who says in front? Raise your hand. That's a good answer because the whole thing is tilted, isn't it? So it has sort of a component of velocity that way, and it might be in front. Who says behind? Raise your hand. Well, that's a good answer too, because after all, the cart is accelerating down the track, just like the other acceleration, right? So the ball should fall behind because the cart is accelerating. Who says in? Raise your hand. Well, only a couple, but that's actually a good answer too, if for no other reason than it's correct. Let's see. It's easy to see that the cart accelerates down the track. It's more difficult to see that because the track is tilted, there's a component of gravity in the direction along the track, one component perpendicular to the track and one along. Therefore, both the ball and the cart are accelerating in that direction. If you tilt your heads so that this direction is up rather than straight up, you tilt your heads, then you'll see that when I do this experiment, the ball will stay directly above the cart, and both of them will accelerate. Everybody tilt your heads. Get the picture now. No, okay. Everybody tilting their heads. Ready? Here we go. Did it work? I think so. It has to, otherwise it wouldn't work this way. This is an unlikely looking contraption. Let's see what it does. Stays here, stays there, stays there, wherever you put it. Doesn't have much friction. If I give it a little motion, it continues in motion. All right. Everybody follow that? Excellent. Got two identical masses. These identical masses. Thank you. Let's see. I'm going to put one on the end and the other one here. And I'm holding this now, so it can't move. And the question is, when I let it go, what will it do? Will that end go down? Will this end go down? or will it stay where it is? What's going to happen? I guess you're all ready to vote. This is a pretty simple one, isn't it? Who says, when I let this go, that the left side over here will go down? Raise your hand. Good Lord, almost everybody. How about the right side will go down? Raise your hand. A couple, they're the ones who are trying to psych me at. How about it'll stay where it is? Raise your hand. Why would anybody say that? Now what's it going to do? Now what's it going to do? This is an interesting gizmo, isn't it? This is a device called a torque compensating device. That is to say, well, it doesn't act like a teeter-totter, does it? If you have a teeter-totter, a single board with a fulcrum in the middle and two people on each end, whichever is about the same size, the one that's further out will go down, or if one's bigger than the other one, the bigger one will go down if they're at the very ends. And this thing is constructed in such a way as to make you think that it's a teeter-totter. It isn't. The fact that this weird construction is used corrects or compensates for all of the torques or forces, meaning that it will be stable here. Actually, what idea in physics is important in how this thing works? Anybody want to try that? Yeah, maybe it's complicated. How many of you have studied the center of mass? Raise your hand. Good many? All right. Wait a minute, that's in the 5th grade, isn't it? The teachers here, right? Okay. Let's see. When I move this, you see, that part goes down by the same amount, this part goes up. This weight goes up by the same amount, that weight goes down. And vice versa. So that means that when I change the position of this, due to the way it's constrained to move here, that the center of mass, vertical position, never changes. So that's what's called neutral equilibrium, isn't it? Something will move only if its center of mass goes down, isn't it? Remember that idea? That's an idea in physics. It's known as the center of mass motion concept, or also you can think of it as an energy relationship, or an energy conservation idea. So this is stable, no matter where I put it, because the center of mass doesn't go down. If I put this extra weight on that side, now what will it do when I let it go? That side goes down, doesn't it? Because there's more weight going down than going up. So the center of mass goes down. How about if I put that over here? Now what will happen? Yeah, this side goes down, doesn't it? Does it? Yep, sure does. Because more weight goes down than goes up. For those of you, anybody here in high school? High school physics, right? The way you solve this mathematically, if you're a physics student, is you write 12 equations down. Yeah, 12, one for each of the moving points here. 12 equations, and you solve them simultaneously. Right? That's a little complicated. But it turns out that if you write down all 12 of those equations, it's the same equation 12 times. It's impossible to solve this equation, this thing, mathematically. You can't do it. Only by intuition. Just what we've done today. That's the way you solve this problem. Interesting idea. By the way, how many of you have actually used a device like this? Raise your hand. No one? My goodness. I thought you all would have. Because it turns out that that's the mechanism in a pan balance. A pan balance is very close to this, with two exceptions. One is that the pan is rigidly attached to these vertical sides. Goes straight up and then the pan here. See that? And the second thing is that this top beam is sloped a little bit. So I'm going to be the pan balance. My fingers are the fulcrum. My elbows are the pans. So if you put the same weight on both and then rotate it, let's see, rotate it back and forth, the one that goes down doesn't go down as much because they're rotating about my hands. The one that goes up goes almost straight up here. The one that goes down is curving on like a circle, isn't it? So whichever side, it gets unbalanced. So this is in neutral equilibrium. It'll stay wherever you put it. And a pan balance will balance with both sides sticking out the same way if there's the same weight on both of them. We just happen to set it up here that way. Here it's set up so that the, just change positions with this. You can leave that on there. Here it's set up so that there's a beaker of water on one side and a couple of weights on the other side. It's actually in balance now. I can make it go either way, or here it's in balance, like that, okay? And here's the question for this now. I'm going to go up to the beaker and stick my finger into the water. What will it do? Will the side with the water go down? Will the side with the weights go down? Or will it stay balanced when I put my finger in, about the first knuckle? Water down, weight down, or stay balanced? All right. Seems like there's a difference of opinion. Let's vote. Who says, when I put my finger in, the water side will go down? Raise your hand. Okay, a few there. Whoop, a few more. Delayed reaction. All right. How about the weight side will go down? Here, raise your hand. Nobody, oh, hardly any there. Okay. How about it'll stay balanced? Okay, about 86% there. All right. It'll stay balanced. That's the vote? Okay, let's do it. What did it do? The water side went down, right? So now we got to think of why. Let's see. I think it's called Newton's third law of motion. For every action, there's an equal and opposite reaction. Who all has heard of that before? Good many of you have. You guys see the Nike commercials here that we see in the States? For the Nike gym shoes, they have E equals MC squared and F equals MA on their commercial. I don't know how those are involved, but they have them on their commercial. Let's see. When I put my finger into the water, let's see, what is an experience that you guys have had? You ever sit on the side of a swimming pool or in your bathtub or something and let your feet fall into the water? How many of you done that? Do you feel anything besides wet? Yeah, it feels lighter, doesn't it? Your feet sort of bob up. And that's a buoyant force, isn't it? When you dangle your feet or anything else into the water, they experience a buoyant force, an upward force, and your feet feel lighter than they would normally, don't they? Let's see. That happens here. When I put my finger into the water pushes upward on my finger with a buoyant force. According to Newton's third law, for every action, there's an equal and opposite reaction. So if the water exerts a force upward on my finger has to exert a force back downward on the water. And that downward force is the same as if I took some additional thing and put it on that pan to increase the weight. Except that it's an additional force. The buoyant force, the buoyant force and the reaction to the buoyant force, which pushes down on the water. Interesting idea that you apply a force to something, a force to water by putting your finger into it. Strange, isn't it? That's a hard one to believe. All right. Let's see. Let me, oh. It might help. There is a quick comparison between the so-called Rover ball balance here. Can you see that, or is this in the way? You can see it just a little bit. That's probably enough there. That's fine. Here's the Rover ball balance, and the sticks are sticking out to the side where you hang the weights to make you tricked into thinking it was a teeter-totter. And here's the pan balance. And this is actually a very important idea about the Rover ball balance. How many of you have been to the grocery store? Yeah, a few, okay. Let's see. The clerk puts your cabbage on the pan and the computer reads it, reads the weight, right? And does it matter whether you put the cabbage on the center of the pan or on a corner or along one side? I hope not. I don't think so. That's what this mechanism does when it's used in a pan balance. It means you can put these anywhere on the pans and it'll simply compare the weights rather than compare the torques like it would if it were a teeter-totter. All right. Let's see if we can go back here. Okay. That's it, fine. Physicists like to do experiments, that's right, just leave it there. Like to do experiments with pulleys and spring scales. That's what this is. Here's a spring scale. If I pull down here, I exert a force, and the force is measured in newtons on this scale. 2, 4, 6, here's 5 newtons, 10 newtons, 15 newtons, and so forth. Right? Here's an identical spring scale. If I just hold this up to top and then pull down here, I can also exert a force, 5 or 10 newtons. Let's see, this just happens to be a pulley. So if I pull on the rope that's attached to the bottom of the frame here, it goes over the pulley, and then down. If I pull on the rope, I can also exert a force. Everybody see that? Now I can take this frame and hang it on the upper scale, and now this says that the weight of the frame, this scale, the pulley, and the rope here is about 5 newtons. Right? It weighed, measured 0 without anything attached, and when I put this on here, it goes up to 5. All right. So here's the experiment. I'm going to take this end of the rope and I'm going to pull it very gently until this one goes up to 10. Okay? By the time this one gets up to 10, how far will this one go? Will it stay at 5? Will it go to 10? Or will it go to 15? For example, when I pull this, the string goes up above the pulley, so I'm pulling down on it, but this part of the rope is also pulling back up, isn't it? And those might cancel each other, so this will stay at 5. Or, if I pull and this one says 10, well, I've added 10 newtons here some way, so this should go up to 15, shouldn't it? Or maybe it's somewhere in between, like 10. What will this one read if I pull this until this goes up to 10?
What should it expect?
Ready to vote? All right, let's go ahead and vote. I can hear some of you are still discussing the issue. When I pull this, so this one goes up to 10. Who says this one will stay at 5? Raise your hand. Okay, a good many there. Excellent. How about it'll go to 10? A few? How about 15? Okay, good many more. You ready? Let's see. When I pull down here, I'm pulling with 5 newtons. But if you do an analysis of this situation in physics, turns out there's 5 newtons pulling down on this side of the pulley and 5 pulling down on this. So that's 10 on this lower. Like that. Okay, can everybody see the scale here? Yep, okay. All right, I've got a little frame hanging here with a spring on it. Right now, the scale reads 0. If I pull on it, I can measure the force in newtons. Let's put this frame on here. There it is. And see, it says the weight of this is about 3 newtons. Okay? Here's a ½ kilogram mass, little aluminum mass with hooks on it. What's the weight of a ½ kilogram mass? Okay, if the acceleration of gravity is about, well, it's 9.8 meters per second squared, about 10, let's say, then 10 times a half would be 5 newtons. So if I put this weight on the bottom here, just sit it here, what will this go to? If this weighs 5 newtons, when I put this on here, what will it say? 8. Ah, you're right, okay. Excuse me. Let's do it a little differently. Suppose I hang it on the spring and let it go. What will it weigh then? What will it read? When I hang this on the spring. Everybody have your answer ready? All right, was everybody right? Doesn't matter whether you hang it on the spring or you put it down here on the platform, does it? Let's see. I have a little loop of thread here. Excuse me. What I'm going to do is loop the thread over the hook down here and over this hook at the bottom of the mass and hold them together like this with the thread loop. What will it weigh? What will this read when I get done holding it like that? Everybody got your answer? Oops. Excuse me. All right, were you right? Okay. 8. Now, what I'm going to do Boy. I'm going to burn the string, right? Hold a match right next to it and burn it. When the string burns through and releases, what's the mass going to do? What? Right, it'll start to go up, won't it? What will the scale do? When I burn it and the string releases, will the scale go to a bigger value? Here it's at 8. Will it go like to 10 or 12? Will it go down to 4 or 6? Or will it stay directly at 8? All right. Let's vote. Who says when I burn the string and it releases that the scale will move up to a larger value, like 10 or 12 or something? Raise your hand. None. Higher? Raise your hand. A few, okay. Who says it's going to go to a less number? Raise your hand. Okay, a few more there. How about it'll stay where it is? Raise your hand. Oh, a lot there. Okay. How do these guys in the front row vote? Oh, here it comes again. All right. The light. Okay. All right. Everybody watch the scale. You probably will be able to see when it burns through. What did it do? Went to a larger value, didn't it? In fact, it went to the same number as when I hold it in the same position that the rope was holding it, the little string was holding it before, doesn't it? What happens when it releases? Let's see. The string is actually pulling this down, isn't it? And by Newton's third law, it's also pulling up on this part, isn't it? The string is pulling up here, and it's pulling down here. Let's see. When it releases, and there's no longer a string, the string isn't pulling up on this, but the weight here, this mass, is still pulling down on the spring, and still exerting its downward force on the scale. But there is no vertical force pulling up because the string is gone. So, when it breaks, immediately when it breaks, this force goes up. And then, the whole thing goes back and forth, like that. Because now what's happening is the spring is exerting a force back and forth on this, causing it to oscillate up and down. Strange idea. All right. So we'll do some, okay, yeah, just stick it back over there. Oh. See, we'll sort of change things around a little bit here while, tell you what, here, let's, okay, we'll just, actually, just wing that against there. We'll do this one. Okay, you can't do a good physics program without one of these. This is our tricycle. We've had it fixed. The tricycle is fixed. That is, the wheel won't turn. It can only go forward or backward, right? Forward or backward. It can't turn because we put a little screw here and prevented the whole thing, the handles and everything, from moving. Let's see. If I take this string, got a string attached to the pedal, put the pedal up, hold the string parallel to the ground here, and pull it very gently. What will a bicycle do? Come towards me, won't it? Right? There it is. Everybody follow that? Sure. There it is. Okay. Let's change the experiment. We'll put the pedal down, hold the string parallel to the ground, and pull the same way. What will the tricycle do? Will it come towards me? Will it go away from me? Or will it stay in place and the wheel spin? Low. So what's going to happen now to the tricycle when we have the pedal in the downward position and pull very gently on the rope. Here it is in the up position again. And now there it is in the down position, and when I pull on it, what's going to happen? Who says it'll go forward, just like when the pedal was on top? Raise your hand. A few. How about it'll go backwards? Good many there. Excellent. How about it'll stay in place and the wheel will spin? Well, a whole bunch there. Most of you think that the wheel will spin. All right, you ready? So now we got to figure that out. Let's see. There's the complicated way and the easy way to explain this. Let's do the easy way. Oh, here's my little container for my laser pointer, which I haven't used. All right. If I mark that, the point of the pedal with the laser pointer box, let's see. Notice that when I pull on it, even though, strange, the pedal is coming towards me because I'm pulling it that way, but the pedal's going around like this, which means that the wheel will go forward. Let's see. If you're sitting on your tricycle with one of those little loops that holds your foot to the pedal here, and you want to get started by pushing or pulling on this pedal, what do you have to do when you're sitting on a tricycle? You have to pull it this way, don't you? If you pull it that way, it makes the wheel go around this way and makes you go forward. So it's how you look at it, isn't it? How do you look at it when how do you view the frame of reference of the wheel going around relative to the whole bicycle or tricycle moving along? Strange idea. All right. By the way, if we get our web back, I can show you a couple of neat experiments with that. Oh, no. We'll get it back. All right, let's see. We'll just set that on here. All right, that'll be fine. All right. Okay. This is one of my favorite experiments of all time. I'll tell you a couple of stories about this, because this is really a great piece of equipment. I think you'll like it too. Here's the question. There are two tracks. There's one, there's the other one. Two identical balls. Pool balls, well, almost identical. Now put them in here, and then launch them with the same speed. We'll start with the same speed from this end. Straight track, a track with a dip. And the question is, who wins the race? Will the straight track get there first? Will the dip track get there first? Or will it be a tie? All right. And see, the way I understand it here, almost everybody is voting for a tie. Let's do it by a show of hands just to make sure that I understand things correctly. Who says the straight track will get there first? Raise your hand. All right, that's a good guess, isn't it? Because the straight track, the straight line is the shortest distance between 2 points, isn't it? All right. Who says the dip track will get there first? Few there, scattering. That's a good choice too, because after all, the ball is going to go faster down here, isn't it? Now, it slows down to the same original speed when it gets up here. Who says it's a tie? So, the fact that it goes faster and then slows down cancel each other, doesn't it? So either one of those is a good answer. Now what we're going to do here is a little more experiment like we do in class. There's a technique for teaching physics that I told you about earlier, which involves things like this, called peer instruction, because all of you guys help to instruct and teach each other using this. And what they found is that by using this technique, that students remember more about physics, remember more ideas, remember more the experiments, and it helps everybody to learn and to remember stuff. So, the first thing is, I explained a little bit about this, and you voted. So now each one of you has some idea as to what you think is going to happen. But there are other people with other ideas, and the next important part of the learning process is for you to discuss it with others. So you saw each other vote, so you know who voted for something different from what you voted for. Find somebody different and see if you can convince each other that you are more nearly correct. Okay, we'll take a couple minutes and do that. Talk to the people nearby you and see whether you can convince them that you are right. That the teachers in the front row didn't talk to each other and try and convince each other, their answer, because even though they had different answers. Let's see. Raise your hand if you were able, or if you got convinced by somebody and changed your mind. None. All right. Tell you what. Let me show you a couple of little videos. Can everybody see the top of the screen here? If you argue that the straight track wins, you might like this video. Can everybody see the balls up there? Here, they're going to go down the little incline to get speed. Then they're going to move along together here, and you'll see who wins. How many of you like that video? Not even the ones who voted for the straight track winning? All right. Some of you voted for the dip track to win. No, okay. Some of you voted for the tie. Did you like that better? Do it once more. All right. Now, does anybody want to change their mind? No. Okay. Tell you what. Let me explain. And everybody can see the tracks, right? let me explain what I'm going to think is going to happen, okay? I'll play the devil's advocate and suggest that the dip track is going to win. Wait, let me move this out of the way here. Yeah, that's fine. Just stick it there. Yeah. All right. They're going to start going at the same speed, like this, right together. Let's see, when they come over here, they'll be going at the same speed also, but let's look at the middle now. At this point, let's see, the ball in the dip track is going to get ahead, isn't it? Because it's going to move faster because it goes downhill. See, that's because of conservation of energy, isn't it? That some of the potential energy from up here is converted into kinetic energy down here. So it's going to get ahead. Now let's see. And here, when it gets to this point, it's going to lose energy, isn't it? But what'll happen is it'll get slower, but in the meantime, because it's gone faster in that direction down here, it will be ahead. So the two will move along at the same speed here, and then the one in the dip track will get there first. Right? How many of you hearing my explanation would like to change your mind and vote now for the dip track? None. All right, let's try it. You ready? What just happened? You got swindled, that's what. Let's see. What I said was exactly true, wasn't it? Let's do it again. When the balls were here, they're going the same speed. When they get to this point, the dipped one gets ahead and it slows down, but it's gone faster here. So it stays ahead, and the two go at the same speed here. Let's see, another way to do this experiment is the same kinematically, as far as the motion. If two people, you and I, let's say, are walking along a long, straight, flat path, okay? A long, straight path, just going along in steps, right? Together. We stay together, right? And then, for about 10 steps, rather than go along like this, I go like this, taking a step, but taking a big step rather than a small one. I get ahead, don't I? Then, after taking 10 big steps here, I start to take small steps just like you did. Does that put me back where you are? You're still ahead. I would still be ahead, but moving at the same speed. And that's the same thing that happens here, isn't it? Everybody follow that? Do it once again. Absolutely. Let's see. One of the reasons why I like this is that most of the time when I show this to physics professors, in fact, just last month, the beginning of last month, I gave this program, almost the same experiments, to a group of about 80 physics professors from American universities. And their results for this experiment, the various answers, was about the same as yours. Interesting idea when you think that you guys have had on the average 0 years of physics, and these physics professors have, let's see, 4, 5, 5, 10, 11, had 11, and then maybe some teaching, maybe 12 or 14 years of physics experience. Interesting idea. I wonder how that happens. But even more important, doesn't this show you that if you want to learn physics, you got to have equipment, you got to have a piece of experimental apparatus there to show you. After all, how would you know that it didn't happen like this, especially when you saw the 3 little videos? Could you tell what was wrong with those videos that made this not correct for 2 of them? It's unlikely. It's very realistic, isn't it? In fact, this guy, the name here, Tom Thaden Cook, wrote a PhD thesis using this apparatus and analyzing how people react to it and how they learn from this thing. Very interesting idea. Another experience that when I took this to a university, another university in Maryland, and gave this program and showed this to them. And about 2 years later, an article appeared in one of the physics journals, the Physics Teacher magazine, probably none of you have heard of it, saying that it was incorrect. The guy did an analysis using a bunch of computer calculations like these, only he was serious. He thought that this was wrong. It's absolutely correct. He was wrong, and he was a physics professor. Interesting idea. There's a lot of neat stuff you can argue about and think about, and some of it is really, you can get into good arguments, right? And a good argument about physics is the best way to learn physics. Also helps prepare you for marriage. All right, good. So let's put this down. Okay. Stick it down at the bottom of the slide. All right. Let's see. How much time we have? Come on, you guys have all studied one. All right. Good many of you. All right. Everybody see our apparatus here? This problem is called the rock and boat problem. Believe it or not, I guess it was 60 years ago now. When I was a little kid, I remember arguing about this problem. I don't remember the conclusion that we came to. In fact, I don't even remember whether we even came to a conclusion. All I remember is arguing about this problem. I guess that's what's the important thing, isn't it? Here's the problem, called the boat and rock problem. Here I have a boat. You can see the boat in here. The water's a little murky, but that's right. And there's a rock in the boat. It's a lead brick, a little tiny lead brick. Not so tiny. And the rock in the boat is floating on a little pond. Okay? The water in the pond is up to a certain level. See the red marks here? Right at the top of the red marks. Can you see the water? Water level at the top of the red marks. Okay? That would be like you're out in a boat, in a rowboat, in the middle of a pond, and you have a great big rock in the boat, and on the shore, a friend, it's a rocky shore, so a friend goes up and right at the level of where the water is, makes a mark with chalk or maybe paint or something that won't erase, that won't wash off of the water. Right? Makes a mark on there, and the water is at a certain level in the pond, with you sitting in there in the boat with a rock, a heavy rock. Now, here's the thing that you do. You take the rock when you're in the boat. Doesn't matter, you can't lift this much rock or anything. You take the rock out of the boat and throw it into the water and it sinks to the bottom. Okay? The question is, what happens to the water level in the pond here? When you throw the rock into the pond and it sinks to the bottom, does the water level in the pond go down? From here down like this? Does it go up? Or does it stay the same? I already hear all three different answers. All right. You ready to vote? Yep. Okay, let's vote. Who says when you take the rock out of the boat and throw it into the water and it sinks to the bottom, the water level in the pond will go down? Raise your hand. Okay, good. Who says the water level in the pond will go up? Raise your hand. There's many there. Who says the water level in the pond will stay the same? Yeah, good many there. Actually, going up seem to have a little bit more than the others. A lot of group in here that isn't voting. I'll talk to you later. Let's see. I guess we've got to do the experiment to determine this, don't we? Let's see. We'll take the rock out of the boat. Here's the lead brick, and I'll let it sink to the bottom. Is the water level higher, lower, or the same? It looks to me like it's down here now. Isn't the water level lower? Yes. I think so. Let's see. How many of you know the 2 laws of buoyancy? At least one of you. I am right. There are 2 laws of buoyancy. Yeah, okay. Let's see. It says that when something is floating, it displaces its weight in water. When something sinks, like the rock right now is sunk, it displaces its volume in water. How many of you remember those 2 laws of buoyancy? Anybody? Nobody. Maybe the education system in India isn't any better than it is in the United States. I do this experiment on this program when I go to classes where they've just studied buoyancy. After they've immediately after they studied buoyancy, most of the students will be able to tell me the laws of buoyancy. You just said it. Unfortunately, there's another little detail, and that is, see, when something floats, it displaces its weight in water. When something sinks, it displaces its volume in water. But they forgot to tell the students what displacement means. Key ingredient, isn't it? Let's see. When this boat is floating up here, when I push the boat further into the water, it displaces more water. So the water has to have somewhere to go, so it just rises in the pond, doesn't it? Right? The more water I displace, the higher the water level in the pond is, isn't it? Everybody see that? Yeah. Right now, it's the rock here, the lead brick, is displacing its volume in water, isn't it? It's pretty small, isn't it? Not a very big lead brick. However, its weight, pretty heavy, lead is. So when I put it and let it float, it displaces its weight in water, which is much more water. The boat goes further into the water, and therefore the water level in the pond gets higher. Interesting idea. Actually, this is pretty important too, because if they take an ocean-going boat and fill it full of something, grain, oil, steel, whatever, there's a line on the boat that says you can't make the boat get any lower than this or it'll sink. That's bad. You don't want to do that. So you put it to the line, and then if the boat goes into a freshwater surrounding, like a river, goes up a river somewhere into the Great Lakes in the United States, it's in a lighter water, therefore it will sink lower in the water, displace more water, and go above the little marks on the boat and sink. So you have to know pretty carefully about when you're transporting stuff, about how the level of the boat in the water is going to change when you go from fresh water into salt water, or salt water back into fresh water. Actually very important. All right, good. All right, thank you. Well, let's see. I think we have, oh, here, okay. I think we have enough time for 3 more fun experiments here. Let's start with this one. I have 2 identical balloons. You can tell they're identical because they're both yellow. Yeah, you're right, that was a joke. Put it a little further on the plastic tube. It's not supposed to do that, is it? All right, there it is. Oh. There it is. The clamp is holding the air in there. Blow this one up a little bigger, put it on the other end here. And now notice that the clamp is holding the air from moving from one balloon into the other if it wanted to. The air may not want to move. The question is, for you, what's going to happen when I remove the clamp? So the air can move if it wants to. Let's see. Will a small balloon get smaller and blow up the big one? Will they become equal? Or will they stay the way they are? What are the balloons going to do? Will the small one get smaller and blow up the big one? Will they become equal? Or will they stay the way they are? Ready to vote? Okay, let's vote. Who says when I release the clamp so the air can flow if it wants to, the small balloon will get smaller and blow up the big one? Raise your hand. High. A few, okay. How about they'll become equal? Raise your hands. Oh, a lot there. Okay, looks like about 87% of you. How about they'll stay the way they are? No change. A few there. Okay. Let's see. Before I do it, let me ask you a question. When you blow up a balloon, how many of you have blown up a balloon? Raise your hand. Okay, good. When you blow up a balloon, when is it hardest to blow up? When is it hardest to blow? At the beginning? Okay. All right, having asked and answered that question, you want to change your mind. Let's vote again. Who says that the small one will get smaller and blow up the big one? About the same, maybe a few more. How about they'll become equal? About the same and stay the way they are? Uh-oh. Now some of you have been subject to a certain amount of doubt, I guess. They stopped voting. All right, you ready? Let's see. When you blow up a balloon, it's harder to blow when it's small, isn't it? You all said that. That means that the rubber is thicker and it's curved more, sharper curves. Those two things together make the surface tension more. That is the ability of the balloon to push back on you. As it gets bigger, the rubber is thinner, you can almost see through it there, and the curves are bigger. Those two things mean that it has less surface tension, so a small balloon will always blow up a big one. This experiment also works for soap bubbles. It's exactly the same, and it's a soap bubble experiment. All right, good. When I heat this plate up, this is a brass plate, very thin brass plate, square brass plate. When I heat it up, the brass plate expands, gets bigger. This brass plate just happens to have a hole in it. And the question is, when I heat this brass plate up, will the hole get bigger, smaller, or stay the same size? I guess the question might be rephrased as, what happens to the hole? How does brass expand? Does it expand outward here, and does it expand outward into the hole? How does it work? Right, but the question you have to answer, will the hole will the hole get bigger, smaller, or stay the same size?
Smaller.
Let's vote. Who says the hole, when I heat this up, the hole will get bigger? Raise your hand. Few there, hearty souls. Okay. Who says the hole will get smaller? Of course, the brass expands in both directions. Who says the hole will stay the same size? These are the wimps. The people who are afraid to go on one side or the other, they just say it's going to stay the same size. Let's see. We need to have somebody, I need a helper, sorry. You want to? Okay. Tell you what. Let me prepare the experiment here. Let's see. And what I'm going to do now, we'll measure the size of the hole, and then I'll heat it and measure it again. And the idea is, can you feel the size of that hole? Sort of feel the hole with your hand, with your finger. And then I'm going to heat it up. And he doesn't want to do that. I'll tell you what. Okay, you're not a very good helper. So we'll use another way of telling the size of the hole. This ball, which
Just fits.
doesn't go through the hole. All right. So let me heat the hole, the ball. No, heat the plate, and we'll do a thought experiment. Einstein did thought experiments and then learned a lot from them. So we'll do a thought experiment and learn something about it, and then while we're heating it. So suppose that rather than having a hole there, I just have a plate with a little circle drawn on it, right? Now, will the region, when I heat it, will the region inside the circle get bigger, smaller, or stay the same size? Get bigger, won't it? Just a piece of the plate, just like the rest of the plate. So if I put a crack there, and the material can be taken out, if I take it out when it's cold, then take it out when it's small, will it be bigger, smaller, or the same size? After it's hot, it'll be bigger, won't it? So the hole has to be bigger. Thank you. Let's see. This idea is known as linear thermal expansion. Any 2 points on this plate, the side, one side, the other side here, a diagonal across the whole thing, or the diameter of the hole, all expand by the same ratio when you heat it up a certain number of degrees centigrade. Linear thermal expansion. By the way, I'll bet you that, especially the kids, that probably your grandparents know that. Where would you use this idea? Right. Suppose you eat bread with jelly on it for breakfast around here. I think so. And you have a glass jar with a lid that you screw on. And sometimes the lid gets stuck, doesn't it? And what do? You heat the lid in, let it hot water, right? Turn it upside down in some hot water, let hot tap water. It expands, gets bigger and easier to unscrew. That's the idea of linear thermal expansion. You do that here, don't you? Not just in America. Okay, good. So everybody knew that one. Now, we got one last experiment for you. When you look at yourself in a plain mirror, like this, I brought one along just to, When you look at yourself in the mirror, how would you describe your image? How would you describe your image? In physics, besides beautiful. Let's see. In physics, we describe our image by what the optical system, like a mirror or a lens or something, does to it. For example, when you look at yourself in a mirror, is your image inverted top to bottom? No? Wait a minute. Is your image inverted left to right?
Yes.
Is your image inverted front to back? Or is your image not inverted at all? Those 4 questions, you can say yes to any number as long as you're consistent with yourself. How is your image inverted when you look at yourself in a plane mirror? Let's start. Let's just take a vote here. Who says your image is inverted top to bottom? Raise your hand. No one. This group knows which end is up. That's good. That's an old American saying. Old Indian saying too, I guess. Right. Who says your image is inverted left to right? Raise your hand. Oh, a good many there. All right. Who says your image is inverted front to back? A few. How about your image is inverted? Not at all. There are no inversions when you look at yourself in a plane mirror. Raise your hand. Okay, good. Now, to answer this question in physics, one thing we can do is to use coordinate systems. If we want to explain where something is, we use a coordinate system with 3 coordinates, x, y, and z in 3-dimensional space. Use x and y in 2 dimensions on a piece of paper. In 3-dimensional space, x, y, and z. Here it's red, white, and blue, where x, y, and z. This is a right-handed coordinate system. If I make my fingers rotate from x to y, my thumb points in the direction of z. And I'm just going to put this down here in front of the mirror. Let's see. Here's another one. I need a helper. Another helper here. Maybe one of the students. Oh. Here, let's get a student here. Ah, here she comes. Okay. Good. All right. Good. What's your name? Prita. Oh. Prita. Okay, excellent. All right, Prita. You can see this image, or the mirror, the coordinate system and its image. Maybe what you're going to do, here's an identical one. So hold this up above and orient it so that it looks the same as the one that's in the mirror. Can everybody see the one in the mirror now? Prika is going to rotate that so that it looks the same as the one in the mirror. Don't look at me, you're supposed to look at me. Yeah. Or make it oriented in space. No, you got to hold it up here. Don't. So that it looks the same as the one in the mirror. Is that right?
No, blue should go back. Blue.
Something wrong, isn't there? What's wrong? The blue one going in the wrong direction? Tell you what, Rika. Here's a left-handed coordinate system. It says the red and white ones are the same, but the blue one's going in the opposite direction. Try that one, see if you can line it up. Is that right now? Okay. Can anybody look at the thing now and see a problem? Maybe not. Thank you. Excellent. You can't do it with the same one because the one in the mirror is inverted, has one inversion. Therefore, you have to have a coordinate system with one axis pointing in the wrong direction, the opposite direction. Let's see. And that means that there's one coordinate that's inverted. We ought to be able to study that. Can you see the coordinates? See the See it now in the mirror? Yeah, put that down. Now can you see it? Let's see. Look at the red one. In the, oops, where? Wait a minute, what am I doing?
Put it flat, you can take the time.
Oh, there it is. Yeah, there it is. All right. The red one in the flash here is pointed to your right, isn't it? In the mirror, what direction? To the right. It's not inverted. The white one is pointed up. In the mirror, up. That's not inverted. Everybody agreed that the white one was not inverted. Everybody agreed there's no inversion up to top to bottom, right? Let's see. Here's an interesting question. If the mirror inverts the image top to bottom, but not right to left, or it inverts it right to left, not top to bottom, then to fix it, all you'd have to do is change the mirror, wouldn't you? Nah, can't do that. No inversion at all. But what is inverted? In the flesh, the blue one is pointed that way, isn't it? What direction in the mirror? That way. Your image is inverted front to back in a mirror. Otherwise, let's see if I can find this. That's what your image would look like, isn't it? Is that right? There's your image in a plane mirror if you're not inverted front to back. I think. Everybody agree? Thanks. All right. Let's see. Now, here's your quiz. To see whether you just learned something about how to describe an image. Your image in a plane mirror is not inverted top to bottom. It's not inverted left to right. It is inverted front to back, isn't it? All right. Here I have a transparency. What does it say? Right. I'm going to hold it in front of the mirror. The question is, what will it look like when it's in the mirror? What will the reflection look like? Will it be inverted top to bottom? Who says yes, it'll be inverted top to bottom? Okay. Who says it'll be inverted left to right? A few there. Okay. Will it be inverted left to right? Who says it'll be inverted front to back? Raise your hand if you say it'll be inverted front to back. Every hand should be rotated, lifted, right? You just learned that mirror images are inverted front to back. Of course, this is only a plane, so it doesn't matter. Let's see. So what's it going to look like in the image, in the mirror? What does it say? Is it inverted top to bottom? Is it inverted left to right? No, of course not. You just learned that. Now, what many of you may have been thinking is what happens when you have something that's opaque. And now I have to turn it around and put it in front of the mirror. So the question is now, when I do that, right, when I put this in front of the mirror and you look at the image, will the image be inverted top to bottom? Raise your hand if you think yes. Okay. Will it be inverted left to right? Who says yes? Wait a minute. I thought we just decided that it wouldn't be. Well, let's see, let's try something here. All right. Is it inverted left to right? Who says yes? No, of course not. I do need to talk with a few of you about your score, your grades on the IQ test. All right, well, I hope that you all don't feel like the ornithology students. Okay. Everybody knows ornithology? What's that? Study of birds, right? The ornithology student was in a graduate course. After he was working on his PhD, taking a course in ornithology, and it was the final exam time for this student in his ornithology graduate course. And the students were all in class. It was a bigger hall than this. Must have been 400 or 500 seats in the hall. And they were all seated, spread out, the honor system, alternate rows, 3 seats apart. And they were all ready for the exam, and the teacher came in. And he had 200 little tiny boxes, like baby shoe boxes. And each one had a bird in it. And in the bottom of the box was 2 little holes with the bird's feet stuck out through the 2 little holes in the bottom of the box. Every student got their box with a bird in it. What was the exam? Right, identify the bird, right? Well, the feet sticking out through it. And everybody had their box. They were looking at the feet and shaking their box, see whether they could discover anything. And one student came stomping down to the front of the lecture hall, threw his box on the lecture table, said, "Professor, this has got to be the worst final exam that I've had in my graduate school career." The professor was really shocked by this. You don't do that in America even, much less India. The professor was very shocked and stood there tongue-tied, didn't know what to say. And that gave the student more courage. He said, "In fact, your class in ornithology has been one of the worst classes that I've ever had in my college career." And the professor now was really shocked. And again, even worse, didn't know what to say. He started to sweat a little, and his face was getting red. And that gave the student more courage. He says, "In fact, you are without a doubt the worst teacher that I have ever had in my life." Now the professor was really shocked and just couldn't say anything. The blood vessels in the tongue and the neck were sticking out, and sweating. And finally, he regained his composure, looked at the student and said, "Young man, what's your name?" The student says, "Guess." You'd appreciate that. I told that joke one time. I give this program for Physics is Fun, for my public program series that I have. And a lady came up afterwards and said, I heard that joke a little differently. Said, I heard that the birds were in the box, and there was a hole in the end of the box, and the bird's tail stuck out through the box. Well, never mind. All right. I would like to invite you all. We didn't have a chance to do all of the stuff on the web that I was going to try. Our website, physics.umd.edu/lecdem, lecture demonstration. And if you go there, here's my home page, I hope. There it is. This is our home page. And there are a couple of different things which you might want to look at, most interesting to students. First of all, in faculty services, there's simply a list. Here, demonstration index. And this is a list of all the experiments which we have by topic in physics. For example, if you go to kinematics and dynamics, all of the different ideas, center of mass, kinematics in 1 and 2 dimensions, first, second, third law of physics, friction, collisions. For example, in the third law of physics, that covers the ideas of rockets. Here's one. for many of these experiments, we actually have pictures, most of them, and we even have some with videos associated with it. Here's a rocket tricycle. When you push the handle on the fire extinguisher, there's a carbon dioxide fire extinguisher. It shoots the carbon dioxide to your left, out the end of the tricycle, and makes you go forward. And so there's a video of the rocket tricycle in operation. I hope. There it comes. Look, what's that? How do I hear it? Oh, what is this? Where's backwards? Oh, way up there. Okay, gotcha. Here we go. All right, so you can go there and look at any experiment in any topic, or another one is to go to outreach programs. And our first outreach program is the Physics Question of the Week. And go down here. There are now 300 of these questions, which are like the ones we did today. Each one has an apparatus. We ask the question, give the 3 or 4 possibilities for answers, and then after you have tried to answer the question, you can go to the answer page and see it. I just wanted to try one here, which was, let's go down to they're in 20 question archives. Here's archive 1. And the question up here, actually a lot of these are ones that we use today. The balloon one, the racing balls one, the Rover ball balance, funnel carts, the drop slinky, reaction to buoyant force. Let's see. Here's the racing ball question. It shows a picture of the apparatus. Here it is. And then asks the question, what will happen when you start the 2 balls with the same speed? Will the ball on a straight track win, the ball on a dip track win, or a tie? When you guess, then, you go to the answer. And now here's the answer. It tells the one that wins is the one with the dip track. And you click on this, and a video of the action comes up. Yep, here. And it shows in educating, at least getting their students to argue about physics. All right, so anyway, you're welcome to visit our website and to use any of the apparatus or any of the information. Nothing's proprietary. You can feel free to use it. And I hope you enjoy it. Thank you very much.